Hello class, so this is CSE-5250 Section 2 Week 14, and I hope you're having a good Thanksgiving by the time you're watching this, or you've already had a good Thanksgiving. For this video, I want to show two things. The first one is a CUDA implementation of one of the Pythagorean theorem problems that I showed. The second one is a sample of what kind of problems to expect on the final. So, let's begin with the Pythagorean triple finder. Now, if you don't remember what this was, or if you need a refresher, this is a program that all it does is find Pythagorean triples, but it does so in a rather more efficient way compared to the one we had previously. So, this is the one we made parallel sometime before. So, if I just remove those pragmas, if you remember, this program is using a triply nested for loop to look for Pythagorean triples. It turns out there is a faster way of finding whether a squared plus b squared equals c squared. And it does not require this inner for loop at all. So, basically here's how it works. If I have c squared and have it equal to a times a plus b times b, well, that by definition that's c squared. But what I want to know is what I want to know is whether the square root of that is an integer value. So there is an easy way of doing that. So and here's how. First, I'm going to make a double and call that c, and assign that to be the square root of c squared. Okay, now we have the c value as a double. Now what? Well, here's the thing. If c squared if its square root really is an integer, then its fractional part, the stuff that comes after the decimal point, that should all be 0. So what I'm going to do is declare another integer value called int c floor. And I'm going to declare this to be, I have to cast it to int, but I want it to be the floor of c. And now I just need to take the difference between c and c floor. And I should get the fractional part of c's. Yeah, I should get the fractional part of c. So I'll declare another double and have that equal to c minus c floor. I'm going to call that the fraction. Now, if not, fraction is greater than 0.0, if the fractional part is not greater than 0, then I can say that we have found a Pythagorean triple. So I'll just copy all this. And just like that, we don't even need the inner for loop anymore. So what I've done is optimize this for loop, so instead of being a triply nested for loop, it's a doubly nested for loop. And it works. Kind of. Because I removed all parallelization from this thing, the program has no idea what OMP get. It doesn't. Okay, what I'm trying to say is, I originally had this print statement print out 4 values, and one of them was the thread number, but we're not dealing with threads anymore, so. Or rather, we don't have multi-threading anymore, because I removed it. So really I have to do that. And now, hold on, that's not quite right. That's because I actually need C floor. And now if I run this, it should work now. There we go. 3, 4, 5, 5, 12, 15, 8, 15, 17. Those are the Pythagorean triples that I've memorized. So, 3 squared plus 4 squared equals 5 squared. 5 squared plus 12 squared equals 13 squared. It also means that 3 squared plus 4 squared plus 12 squared equals 13 squared. But anyway. So yeah. The reason why I bring up this square root and find the fractional part of a floating point number is I use this the same way with the CUDA implementation of this Pythagorean triple finder. So let's look at that. Okay, so let's look at the main function first. So I have it so that I'm looking for Pythagorean triples whose A and B side lengths are up to 10,000. I'm using an array that's representing a 2x2 grid. No, a 2-dimensional grid, and it's 10,000 by 10,000 elements. So, if you can imagine a table where one column represents the side length A, and another, a 2-dimensional grid where corresponding rows correspond to A's side value, and corresponding columns B's side value. Wherever those intersect correspond to a possible Pythagorean triple. And what I'm going to do is this. For every Pythagorean triple where c squared has a square root that's an integer, I am going to put c in that entry on the table. Otherwise, I'll leave it as 0. So if you can imagine a table where we have like this. I don't have my tablet right now. Anyway, so this would have a value 5. And these values here would not have anything in it. Actually, this value here would also have a 5 because... So yeah. Another way to think about this is a grid in which you can actually draw triangles. So yeah. This is how we're representing the array that contains all of our triples, but I have it so that it's a 1-dimensional array instead of a 2-dimensional array. So, well, first off, I have to allocate all the necessary memory. So I pass in the address of triple search max squared, which is 10,000 times 10,000, times however big an int is. And then I call the kernel. I launch the kernel, and let's see what's happening in here. Okay, first I need to calculate the thread number, the thread count, the block number, and block count. Now, because I'm iterating through this 1D array and pretending it's a 2D array, I need to make a few extra calculations. So, here's how it's done. Side length A is going to be calculated as such. It's I from this for loop here, mod search max plus 1, because it'll just give me an answer that's offset by 1, and I don't want that to happen. For B, it's I divided by search max plus 1, and this is integer division. So if, for example, we have a 100 by 100 grid, index 204 would actually correspond to the 345 Pythagorean triple. Let me just pull up that picture again. So if this is 100, and this is also 100, then this matrix is actually a 1D array filled with 10,000 elements. This element right here would be element 203. And this one would be 300. I believe this one would be 302. Yeah, because these are 0, 1, 2, 3, and then 100, 100, 2, 100. Yeah, 0, 1, 2, 3, yada yada yada. 100, 101, 102, 103, and so on. 200, 201, 202, 203, and then 300, 301, 302. So yeah, I can get the side lengths as A equals I mod 100, and B I integer divide 100. But of course I have to add that plus 1 so the math works out. So yeah, that's what's going on with this. Use a 1D array to represent a 2D array. Not unlike the matrix multiplication example I showed. So, how do we determine whether a number... No, how do we determine whether a number's square root is an integer? Well, we employ the same trick as before, where we find the square root as a double, round that down to an int, subtract the square root from no. Let me start over. To determine whether c squared has an integer square root, we calculate the square root as a double. We then calculate c floor as c, but rounded down to the next int. We calculate the difference between c and c floor as the fractional part of c. If that fractional part is greater than 0, then that is not an integer solution. If it is the case that we have an integer solution, I'm going to put, if this was element 203, I'm going to put the number 5 in it. Likewise, if it was element 302, because redundancy, I'm still going to put the number 5 in it. So, let's see this thing run. Oh yeah, before that, I also have to print out, I'm also going to print out all the triples that I found this way. That's after the CUDA device synchronized, and then after that I'm going to free up all the memory. And that would be the end of the program. So, let's try it out. took a bit of time, but it started to print out all the solutions. And there we are, 345 and 435, because if you think about the entire possible space of Pythagorean triples, you're gonna have some redundancy where A and B are swapped. So what we really could do, is cut the possible space in half. Yeah, there's probably a way of cutting the possible space of Pythagorean triples in half, so you don't have to deal with ABC versus BCA. Also, there's probably a way of eliminating multiples of Pythagorean triples, so 6, 8, 10 is basically the same as the 3, 4, 5 triple, but multiplied by 2. So we're gonna see some redundant copies in the form of their multiples and their swaps. But anyway, we did end up finding a whole bunch of Pythagorean triples. And a bunch with the side length 273. So 136 plus 136 squared plus 273 squared equals 305 squared. So yeah, it works. I'm gonna close that. There we go. It's gone. Alright, so a way of playing around with this, I encourage you to do so, because to program with CUDA and get results this fast is actually quite fun. Anyway, I'm going to skip ahead to the final sample problems. Right, so these are problems I would probably ask you on the final. By the way, I'm going to make the final available on the Wednesday of week 15, and it will be due during finals week. So basically, you should have more than enough time to finish that. It's a take-home final. I'll post a few more instructions as we get closer to that day, but that means we should have no more new content on week 15. But you are welcome to ask questions if you have anything else that needs clearing up, or you're confused about a concept or whatever. Anyway, let's just look through these problems together. And okay, this is one where we have to make a parallel for loop, but all we need to do is to fill in the blanks for the for loop. So here we are. Well, the first one is without any parallelization, and the second one is with parallelization. So this is problem 1. Problem 2 is basically, look at this program. Can we make it parallel? Problem 3 is more of the same. Problem 4 is Amdahl's law. And problem 5 and 6 are just small conceptual things. What are the differences between processes and threads? And what are the differences between data parallelism and task parallelism? I should also have this file available on Canvas. So basically, the rest of the video is a walkthrough on all of these questions. So if you want to try these questions for yourself, you can grab the file and you can pause the video right now and have a crack at it. Okay, so as I said, the rest of the video will be devoted to walking through what's going on here with these problems. Walking through them so we can try to solve them together, so we get an understanding of what's going on. Okay, so let's start with the first one. And I should have an answer guide for this sometime over the break as well. Suppose we have an array where every 2 elements are needed in a calculation. So I have A1, B1, A2, B2, A3, B3, A4, and B4. So here, we need to fill in the blanks for the for loop declaration below. And this is without any parallelization. Let's also assume that array length is already defined as the length of the array. So, how do we solve this? Hold on. Okay, I got my tablet back. So, this first for loop is basically no parallelization at all. So we're gonna be iterating through the entire array. So really what we need to do is say that we start at 0. Whoops. And since we have to iterate through the whole array, we just have to say for int I equals 0, I is less than array length. And then I don't have an I++ because it turns out we need to use every 2 values. So every 2 values is used in a calculation. So we have something like this. That's because we have, if you have the array, if you have I starting at element 0, we also need the element after that. But it also means we can't increment to the element after that because then we'd be getting all the wrong values and they're offset from one another. We'd be getting B1 and A2 and that's not what we want. So we need to increment by 2. So here. This is not unlike a few calculations that involve, say, you got an array of RGB values, and every 3 values is used in a calculation. It's not unlike that. So yeah, here we have our for loop, where we have to iterate through the whole array, but every 2 values are needed in a calculation. For int I0, I is less than array length, I increment by 2. But suppose we wanted to make this parallel. Suppose we had, say, 2 threads, thread 0 and thread 1. Now what? How do we have it so that each thread does different work, but they're not overlapping each other's work? Let's say we have thread 0 start here. But because every 2 values are needed in every calculation, we need T1 to start here. We can use their thread IDs as part of this calculation as well. In fact, we can assume that thread ID and thread count are already defined. And thread ID is, well, the thread ID, and the thread count is, well, the number of threads that we have. So thread ID is going to be equal to either 0 or 1 because this is going to be executed on separate threads. And each thread is going to have its own ID. So it's either going to be 0 or 1. Thread count is, well, we have 2 threads, so that's going to be equal to 2, no matter what thread we're on. So, because we have threads 0 and 1, we can just say thread ID but that would be half the answer, because if I multiply thread ID by 2, what happens is T0 is going to still start at index 0, but T1 is now going to be offset so that it instead starts at index 2. So really, thread ID times 2. That's the first blank. For the second part of the for loop, we have to iterate to the whole array no matter what. It doesn't matter if we're incrementing by 1 or 2 or a million. So the answer to this second blank is the same as the first blank, actually. So array length. Okay, but consider what happens when we want to go to the next loop iteration. T0 has to skip over whatever work T1 has already did. And T1 has to skip over whatever work T0 is going to do. So T0 is going to leapfrog to here, and has to skip whatever T1 did, and T1 has to leapfrog to here, and skip whatever T0 is going to do. So, it's not enough to just say I plus equals 2, because we have to also multiply it by however many threads there are, and that's actually the answer. Since every 2 values are needed for a loop iteration, we have to skip 2, but then we have to skip 2 times however many threads we have. So it's thread count times 2. And that's the answer for number 1, actually. So yeah, this is basically the principles of how to make a parallel for loop if you didn't have the luxury of something like OpenMP. If you had to write this thing out for yourself, not unlike with how we have our NVIDIA CUDA examples where, for example, here, I have to calculate a start index and a stride based on, for the start index is actually the thread number times, no, the thread number plus however many blocks I have. But, yeah. If it's the case that I don't have any blocks at all, this example only ever had 1 blocks. Yeah, only 1 blocks. If it's the case that there's no blocks at all, because NVIDIA CUDA works with blocks and threads, we can just ignore this and say that the start index is whatever the thread number is. And then we can say the stride, because we don't have blocks to deal with, the stride is the block count. No, the thread count. If we had, for whatever reason, 2 blocks worth of threads, we'd have to add an additional offset, and that's going to be the block number times however many threads we have. So if you have threads 1 to 100 on block 1, and another set of threads 1 to 100 on block 2, we have to enumerate those threads such that they're 1 to 100, and then 101 to 200. That's basically what's going on there. But if we don't have any blocks at all, we can just ignore anything that says block. So yeah, not unlike what's going on in CUDA, not unlike what we had to work with MPI, the magic of OpenMP is all of this is abstracted away for you, so you don't ever have to worry about it. You just slap in that compiler directive and that's it. What's going on here? Can we make this parallel? If not, how? What's going on here, anyway? Okay, so we have 2 integer values, 300 and 17. We have 2 more, that's going to be, well, copies of x and y. We have an increment, and then we have a while loop. M1 is going to be the max. M1 is going to be the larger of the 2 values, and M2 is going to be the smaller of the 2 values. That's what this fmax and fmin mean, and I have to cast them to int for reasons. Then I say that M2 will be assigned to Z, and W will be assigned the value. That's the difference between M1 and M2. So I have M1 and M2 initially assigned to what's basically, they're basically copies of X and Y initially. So what happened here is Z is going to contain the number 17. W is going to contain the number 17 subtracted from 300. So it's 300 minus 17, so that's 283. And then we increment, and then we keep going at this until Z is somehow equal to W. Is this all making sense? Well, it kinda is. What we could just do is just copy paste the entire program into Visual Studio and write it and see what it looks like. Okay, it's just telling me that it's taking 24 loop iterations to all it's saying is it took 24 loop iterations in the while loop. The while loop had to take 24 iterations just to get Z and W equal to one another. So let's take a look inside the for loop by, hold on. Let's take a closer look at the for loop by C outings Z and W. See what's going on now? We're subtracting 17 off of 300 repeatedly until we have a situation where we get a number that's not 17. And when that happens, we do a switch. So instead of 17 dividing 11, it's 11 dividing 17, and then we get remainder 6. But then we switch again, so it's 6 dividing 11, and then we switch again, so it's 5 being divided by 1. And then 1 divided by 4, 1 divided by 3, 1 divided by 2, and 1 divided by 1... No. 5 divided by 1... Let me go back. I kind of got ahead of myself and told what's going on here. It's a sort of chain of division, but every time I reach a number, it's a chain of division where the remainder and the divisor switch places each time. Every time we have repeated subtraction, that's basically division. But I switch the places of the two numbers and start dividing again. So 11 divided by 17 is 6. 6 divided by 11 is 5. 5 divided by 6 is 1. And 5 divided by 1 is actually going to be 0. So there's actually a missing step where instead of this while loop stopping at Z equals W, it technically should stop at when one of the values is equal to 0. But anyway, can you make this parallel? Well, the thing about parallelization with a lot of the for loop examples we've ever looked at is they have loop iterations where each iteration is independent of one another. But here we have loop iterations dependent on the previous iteration, so short answer, no, we cannot parallelize this. But we can make it faster. Here's how. And I alluded to this already. So first, instead of repeatedly subtracting 17 from 300, we can instead say 300 the mod 17, and then we get a remainder. So W should really be Z mod W. And the increment should really be increment plus equals 300 integer divide 17. And when we get to a situation where we have 5 mod 1, we're going to have a situation where W here is going to be equal to 0. So instead of this, W does not equal 0. And in this previous version of the for loop, we had it counted 24. So if you try this specific example again, it's going to skip a few iterations, but in fact, let me pause the video and make a few corrections. Okay, I fixed the for loop. Turns out I had all the wrong values. So this is a slightly faster version of the same exact loop, where instead of repeatedly subtracting, we just replace those consecutive subtractions with an entire division operation. But now we have an answer that's offset from one from the previous example, so we can just do a -1 operation off of that and say that's our answer. So let's walk through this modified for loop, while loop together. M1 is going to be the max value, the larger of the two values. M2 is going to be the smaller of the two values. We assign to Z the smaller of the two values. We assign to W the remainder of M1 divided by M2. We increment by M1 divided by M2, and this is an integer division operation, so we'll always get a whole number. That would tell us how many times we had to subtract 17 from 300, because that's literally what division is. Repeated subtraction, at least for our case with integers. And then after that, we have the remainder divide the divisor, and then we repeat the whole operation again and again until we have it so that we get a remainder of 0. And that's basically what is happening in this while loop. We cannot make it faster with parallelization, but we did make it faster another way, and that's realizing that repeated subtraction is basically division. If you don't understand what's going on here, don't worry too much about it. This is just an example that I came up with that, I'll tell you the truth, this is actually not too far off with how you make microtonal musical scales. That's rather out there topic, to be honest. But anyway, moving on. Okay, so the next problem is basically, it's literally the same thing, but instead we have the while loop in a for loop. We have a for loop, we have a max number of 300. And then we have a for loop where, I enlarged it. We have a for loop where we're going from 1 to max number plus 1. And from that, we're calculating an x and y value, and those become the z and w values for the increment, for this increment and while loop thing that we had in the previous example. Can this be made parallel? Well, I guess there's really two questions to separate from here. Can be made parallel, and is it faster if it's made parallel? No, really, can this be made parallel? we have a while loop inside of a for loop where we have x and y dependent on whatever this I value is. But those iterations only affect the values of x and y are only affect the x and y values only come from the loop iterations, and they don't affect the next x or y values or the previous ones. So it turns out the short answer is this implementation where we have a while loop and a for loop can be made parallel because we can divide this. If you think about all the possible for loop iterations, we can just divide that in half, distribute it to 2 threads, and have 2 threads basically do this while loop operation here. Independently of every possible combination of x and y that add up to 300, and at the same time. So something weird happens when we try to run this ourselves. The answer is, yeah, we can make it parallel, but there is a weird quirk. I forgot the include directives. Let's try it now. Okay, so here's the weird thing that's happening. When we have, if we have the pair of numbers 1 and 299, it's going to subtract 1 from 299 298 times. If it's 2 and 298, it's 148 subtractions. And basically what I'm trying to say is, yes, we can make it parallel, but it turns out the work being done on each thread might not be the same. This is called load balancing. Or rather, what we have is an imbalanced load. So, one thread iteration may be doing more work than another. 298 loop iterations compared to, in some cases, like less than 10 loop iterations. I think I saw it too. Oh, wait, 1. That's probably the midpoint though. Because if we're going through every possible pair of numbers that add up to 300, we have 1 plus 299, 2 plus 298, 3 plus 297, all the way to the midpoint of 150 plus 150, and then the sequence of numbers is basically the same as before, but the order is flipped. So if we started with 299 plus 1, we end with 1 plus 299. So really, technically we've done twice as much work than we need to here. But again, this is just an example of we can make things parallel, but sometimes we get a load imbalance. If I am to use the version of the while loop that we had previously, where I replaced some of the subtractions with divisions, it might run faster, but if you have but only if you have a sequence of divisions where it's the same. No, it would only run faster if you have a long sequence of subtractions, and it's the same. It's the same divisor each time. Divisor? Hold on. It's like, is it the? Yeah, it is a divisor. If you have it such that we have a remainder and divisor flipping places every single time, then it's going to have to rerun the same thing. That's not a string of consecutive divisions anymore. So in those cases, we might have more loop iterations where we have, what I'm trying to get at is it might not be as fast. But I guess what's not really being explored is how not fast. We could put a separate incrementer here strictly for the while loop itself. And if we find out that some combination of numbers required a lot more while loop iterations than the increment suggests, then we have a situation where we have a pair of numbers that somehow results in a thread doing more work compared to, say, the number pair 1 and 299. Anyway, I think that's enough on this problem. It's a bit math heavy, to be honest. So if I'm to ask a question like that on the final, I probably won't have it be this deviously difficult. And so, yeah. The maximum speedup of a parallel program can be calculated using Amdahl's law, where S is the proportion of the code that must be left sequential, 1 minus S is the proportion of code that can be made parallel, and we have n cores. If you have a program that's 70% non-parallel, and I have 4 processing cores, what is our speedup? Well, we can just plug in all the numbers into Amdahl's law, but I feel I have a way of visualizing what's going on. So, let's draw a rectangle and call it 70%. And then we have another rectangle that's going to be 30%. When we say the program has 70% non-parallel code, that's the S. I gotta help myself. So, if you have a program that has 70% non-parallel code, it means the non-parallel, if you have 70% non-parallel code, it means we have 30% parallel code, and that's what the 1 minus S equates to. We also have 4 processing cores. So what happens is, visually, what we do is we leave the 70% rectangle intact, and then we cut this 30% rectangle into fourths. So now we have this rectangle that is basically whatever 1/4 of 30% is, or somewhat confusingly, 25% of 30%. It's basically multiplying fractions with other fractions, in a way. Let's just get us something like half of 30 is 15. Half of 15 is 7.5. So we get 7.5%. So it means the program is running in about 70% of the time that it used to do. But we want to speed up. We want a speed up value. So to get that, we just basically have to divide 1 by 78%. And if I run that through a calculator, apparently Windows 10 has a graphing calculator now, but I just want simple calculations here. So 1 divided, okay, I need a standard calculator here. So if I divide 1 by 0.78, it means I get a speed up of about 1.28. We could just plug in all the numbers into Ohm's law, but I feel like this gives a rather intuitive explanation of what's going on. So if we had 16 cores instead, and yeah, I think I'm just gonna use the calculator on this one, or better yet, I'm just gonna use Excel for this, because Excel is kind of a glorified calculator if you think about it. Okay, so non-parallel code. Parallel code. And Ohm's law says this. So I'm gonna type it in. Oh yeah, I forgot one more parameter, and it's 4. You don't have to use a spreadsheet, but if you to somehow use a spreadsheet on Ohm's law calculations, it's a little satisfying. I'll explain what I mean. So I'm just gonna type out Ohm's law as such. 1 divided by this plus this, and have Excel auto complete the thing for me. So there we go. We get our 1.29 speed up as before. But what if I had 16 cores, 64 cores? What I can do is I can just take the sizing handle and just pull it to the side, and it's not going to give me the same numbers. So what you really need to do is this. And then pull that, and then pull a different sizing handle. Or I can just copy paste the whole thing. And then I can just pull this sizing handle, and it'll auto-fill all the calculations for me. So let's just go for a really big number and say 2048 cores. I take the same percentages as before, and we're not getting much speed up compared to when we had 4 cores. And that's because here's what's going on. This 30% is going to be divided by ever increasing numbers, so really what's going on is this. And the limit as n approaches infinity, this 1 minus s over n is going to approach 0. So eventually we're going to reach a point where all our calculations is basically 1 divided by 70%. So if I get the spreadsheet again and I just say this, but well, there's no more parallel code. We'll get a maximum theoretical speed up of divide by 0 error. And really and the easiest way for me to resolve that is just eliminate that division part altogether. So now we have 1 divided by 70%, and now we have 1.428 such and such. If we somehow had infinitely many CPU cores, and we were able to somehow divide the work among that many cores, the program will ultimately run in 70% of the time compared to if it only had one thread to go around. And that would translate to a speed up of 1.43 such and such. So not much. Basically the point is, if you have a program that doesn't have much parallel code to begin with, it might not be worth the time to make it parallel. Unless you have a situation where you want to squeeze out as much, you want to eke out as much time savings as you can. So it might be the case that you do want to make it parallel no matter what. Or you may want to employ other optimizations as well. For example, this while loop here benefited from us making it parallel using that division operation. But on the other extreme, if you had a program where nearly all of the code is parallel code, just adding a few cores will show an immense speed up. So, for example, 99% parallel code versus 1% non-parallel code. By having 2 cores, you've nearly cut the entire execution time in half. In theory. You also have to deal with overhead and such. But if I'm to ask you this problem on Ohm's law, expect a few changes in values, because when we change the values, we get different possible outcomes. Is what I'm trying to say. On one extreme, you have a parallel program. You have a program with so much parallel code that you can just throw as many cores as you want, up to a point. Or rather, you can have a program with nearly all parallel code, and you can see immediate benefits by just adding a few cores, but diminishing returns when you start to add hundreds of cores. On the other extreme, you have a program with barely any parallelizable code at all, and no number of threads you add will change the execution time, other than the fact that you're probably just adding overhead. 5 and 6 are just minor conceptual things that we talked about in a few PowerPoints. One is the differences between processes and threads. The short answer is processes are basically programs in execution, and they think they have the whole computer to themselves. So how do processes talk to one another? One way is to have a section of memory designated for both processes to share. But it starts to get difficult if you have 2 processes on 2 separate computers, and that's when you start using a message passing interface instead of using shared memory. Threads, on the other hand, are, well, basically they share a lot of the same resource. If you have threads as part of one program, they'll share a lot of the same resources. They'll share the same memory. That's why it's easier to... That's why, as you may have found, it's easier to write a multi-threaded program than it is to make a multi-process program. But yeah. And what's the difference between data parallelism and task parallelism? Well, data parallelism is what we've been doing the entire course when we were using OpenMP and MPI to make the sieve of Veritasities parallel. It's when you have the same set of instructions being done on a really big chunk of data, but it's the same calculation over and over again, so you can just divide the data and have 2 instances of the same code running on those 2 sections of data. That's data parallelism. Task parallelism is where you have one thread that says, oh, I want to do something else. And the easiest way to do that is to have a for loop that says, hey, if your thread ID such and such, do this thing instead. So yeah. maybe what I'll do is um, I'll amend this document with everything I just scribbled in, with a few more notes, and that's going to be the answer key for this set of sample problems. So, have a good Thanksgiving if you're watching this during Thanksgiving break. Week 15, we won't have any new content, but I will give out the final on that week. You should expect to see a final sometime during Wednesday of week 15, and that's basically the end of the course. I hope you had a great time with the course. I hope you learned something interesting, at the very least. And I guess I'll see you later. Alright, thank you, class.